Okay, so first I want to just last time, just to remind you, just a refreshment, okay, what we were doing. We jumped straight ahead into field performance, okay? How do we produce fields typically? These two typical modes, mode A and mode B. And then I have a very important task in the field development process, which is scheduling. And it's not only defining how much and how I'm going to produce, but then at some point I lose control of the field. Okay, you get the impression when you are in plateau mode, I cannot keep a constant rate forever. There will be a time where the system I lose control, and then I change from deciding, from actually controlling, to predicting, simply predicting how much I'm going to produce. Then we said, well, we stop plateau typically because of two things. The system simply cannot produce more, but keep in mind that also we have, because of bottlenecking, okay, we call that bottlenecking. We can have bottleneck in the gas, we can have a bottleneck in the water, not usually in the oil, okay. And yeah, rule of thumb, how do we define this plateau rate? We gave some comments and I referred to the references. And finally, we said, well, let's make first a mechanical analog. So we try to understand how the field works in a very simplistic way. And then we went to using just take that away. We went to make an example. Okay, actually we were using a proxy or a very simplified reservoir simulator, okay, where I need two elements. I said the rest of the system, I'm not going to look at it. I'm going to assume doesn't exist. I don't have any information. I just want to look at the system from the formation all the way to the wellbore, and that's where it stops. And that's typically what in the field development process, what people do reservoir simulation. Okay, they just focus on the reservoir and they use it to generate this production profile, okay, to make production scheduling. And I said we can make our own simulator if we had a few assumptions. Okay, if we say it's homogeneous, it's very well connected, then I assume dry gas to be able to use that equation. And also one other assumption was that it had a very high permeability, such that there are no transient, or the transient is very short, and I can use that equation. And we are going to go a bit back on that, just in a few minutes. But with these two equations, basically they are simply two equations. We can have our own reservoir, very simplified reservoir model. So what we have done in our exercise was, and that's the same procedure reservoir simulator does. Let me just copy the exercise. Exactly, so we first have to find a mystical value that we say minimal flowing bottom hole pressure, which is the minimum pressure that I need to apply at the sand face of the well. Okay, this I think was, did we try 80 or 120? 120, okay, I don't know why it changed. So we said the reservoir simulator, in that step, the first thing it does is substitute that pressure on my equations, okay, on the system of equation. With that, I calculate the maximum, what the reservoir simulator reports has the potential of the well. That's the maximum it can produce. If the rate, and then I calculate, of course, I have a certain number of wells which are identical. Okay, so we are looking at a tank with a bunch of holes, okay, for our proxy reservoir simulator. Okay, and here we say number of wells, and actually we are not looking here. I put like a stick, okay, like a well, but actually it will be just a point. All of them are draining from the same reservoir pressure, but all of them also have the same PWF. Okay. And then I can simply scale up. Okay, the equation was, maybe use this one, QG you prefer this one, or yeah, let's try with this one. CPR minus PWF to the power of n. And then I can simply say that the Q of the field will be n wells times, if all of them are identical, are subjected to the same reservoir pressure, and I'm controlling and having the same bottom hole pressure, then I can simply just, it will be just a multiplier. And that's how I said, well, then I have the maximum the well can produce, I have the maximum the field can produce, and the next checkup that is done is, I say, if what I can produce is bigger than what I want to produce, I simply produce what I want to produce, right? Or if it's the other way, if it's less, what I can produce is less than what I want to produce, then I just produce that. Okay? And then, and here is a very important thing that on that equation, right? So the Q potential, Q field potential, let's make here potential, will be this QF potential, no, just this QF evaluated at when pressure is the minimum. Okay, so it will be n wells and then comes the check. So if Q field, and we call that, sometimes people call it target rate, is a target rate, is smaller than the Q field potential, then simply the Q of the field will be the Q target rate. Okay, in our case, the target rate is the plateau. And what about pressure? What will be the operating bottom hole pressure? Well, I could use simply this equation, right? But now the Q, so I can simply use Q field target rate will be equal to n wells times CPR. But now I just have to clear, I have everything in this equation. I have this one is the plateau rate, I have the number of wells, the C and the N, I have the reservoir pressure, and I simply clear what will be the pressure that I need. Okay, the minimum bottom, not the minimum, but simply the operating bottom hole pressure. Else QF target rate is bigger or equal than QF potential, then simply the Q of the field will be Q of the field potential, and PWF operating will be equal to PWF minimum. So I switch. You have two operating modes, and that people working with reservoir simulator, they work that I'm working at target rate or I'm working at minimum pressure. Those two. I have no other option. So in the example we have made in class, we were doing exactly that. And to do that process in our simulator, we simply put an if. Okay, we made simply a logical operator comparing this potential with the rate that I want. And you saw that, let's see what we found. That was the profile that we found. Okay. And after some point here at year 21, in year 21, we found actually that I can produce around 16 million and I need 20, so I have to change. And at that point, the pressure will be simply fixed, 120 on this minimum. And you can see here, at least from this plot, that the decline was relatively steep. Okay, so I have here a very high plateau value, and then I have, in a matter of a few years, it reaches to the minimum, which I think in that case we had specified 8. Okay, so if the minimum abandonment rate, which will be the rate which is still commercial to produce, I'm still going to get profit, will be someplace here, I reach it very soon. The plateau ends year 20, and then already in year maybe 22, I have to shut down the field. Now let's so one thing we were saying here is that this set factor, okay, we just were a bit running last class, so we just make an assumption that this set factor is equal to 1. In reality, it's not, and we have to use this set. So I'm just going to make now some comments how to improve the calculation, okay, just to improve the calculations, because that's something we're going to see it now, but I have published already one of the mandatory exercise, one of the problem number 1. So you have to do it there properly, not like I did it a bit sloppy, okay, in class. So to improve calculations, Z actually is a function I mentioned before of pressure and temperature. Well, actually, Z, let's go a bit back. If you remember, Z is this factor that I have in the real equation of state relating pressure. This is 1 over density. I have this R, ZRT. Temperature, a gas constant, pressure, density, and this Z is a relationship with that. And I can use that expression for with a high confidence for gas. And this Z is a function of PR and TR, reduced pressure and reduced, not reservoir, okay, small r, reduced pressure and reduced temperature, where these quantities are T over Tc, critical temperature. That's a property of the gas, where you no longer have just 2 phases, gas and liquid, but you simply have like one phase which is very homogeneous. And here you have P over Pc, pressure over critical pressure. And let me just find. Okay, for some of you, you have already seen that, so that's repetition. Some of you, not so much. Okay, like we take that number typically from a chart like that, where we have the Z factor, we have the PR, and we have the reduced temperature. In this exercise, I have given you, to avoid having to go inside the plot, I have given you a function that you can use to calculate this Z. And you have to provide P and T, pressure and temperature. You have to provide the unit if you decide to work for some reason in field units or SI units. But you have to give not critical properties, but you have to give something that characterizes the gas. In this case, I have chosen to use specific gravity. If that's what is specific gravity, how do we define it of a gas? That's a long way to, to kindergarten, right? So you have molecular weight of the gas divided by the molecular weight of the air, right? Molecular weight of the air is 28.97. So it tells you something, and if you remember, the molecular weight of the gas is the sum of the composition, the molar fraction, from I1 to the number of components of the molecular weight of that component. So it really tells you how much, if you have a lot of methane, that molecular weight will be similar to methane. If you have a lot of propane, then it will be heavier. So that is something characterizing the gas. And what we are using inside that expression is listed here on, let me find it, on equation 3 is these two equations, where this researcher, Sutton, he made these two expressions for gas, where he can relate and calculate the critical properties with this specific weight. Okay, so you know where it came from. And then the rest of the, so one part of the equation is calculating that, these two expressions, and then the rest is exactly that chart. Is going into the chart. To go into the chart, you use a special method we are not going to discuss very much here, but here is the whole procedure. Okay, that was made by Hall and Yarborough. That's a difficult name. And they convert the chart on an equation. And then you don't have to go in the chart every time. If you are interested where it came from, maybe I can copy that so you have it. I hope Curtis Whitson, he doesn't sue me for just stealing material from him. He's sitting very close, so he can take action if he wants. But just to clarify, this set factor, you know, where it comes from, and you can simply use the equation. Okay, in our here set, instead of just putting 1, you call that function. It was C factor standing, and then you have to provide pressure, and that will be reservoir pressure. Temperature, you have to select that one here, and you have to block it. Specific gravity of the gas, this one, you see is half of the air, so it will be around, if the air is 28, it's around 15, 14, so it's very much methane-like. And the unit here you have to remember, I think, is 2. And you get, instead of 1, 96. And you tell me, well, it's not a big deal, okay, it's a small difference. Why do you care so much about this set? If you see set is affecting pretty much, is multiplied, where do I have it? Okay, it's affecting very much the decline of the pressure. Okay, and a very small change, and P usually is a relatively big number, can make a big change in the pressure. Okay, so don't neglect, even if it's a few percent that you say, well, it's not much, it can have a big effect on the then I drag it down. What happened here? I have to fix this one. Yeah, good that you're awake. It looks like I'm not. Okay, so that was one thing that I said, you know. The other thing is the integration method we are using. Okay, that's one improvement we, you know, I don't think you have to do it for the exercise, but something you have to think about. When, let's say we have a profile that looks like that. And what we are making to approximate this curve, so that's Q of the field, or Q gas versus time. What we are doing to approximate that curve, basically, we are taking that the value of rate that I calculate at the initial time will remain constant throughout this period, this delta t. It will remain constant, then the next one that I calculate will remain constant, and that's very fine for the plateau rate. But when you reach, let me just make it very quickly, but when you reach the end of the plateau, then you see that it's not a good approximation anymore, not such a good approximation anymore. And actually you have an overprediction of this GP. And it's like a chain reaction. If you have a bad prediction of GP, that gives you a bad prediction of reservoir pressure, and that gives you a bad prediction of the next rate, right? Here I have some NP, right? That will be poorly predicted. With this NP, I poorly predict a PR, and with this PR, I poorly predict a QG. So it's like builds up. So a better approximation, a much better method, okay, is what we call the trapezoidal rule. That what does it say? Again, is this math from Barnehage? Okay, that you have a function f1, then you have f2, x1, x2. Let me make the axis such that we can see what we are talking about. Okay, so how do we, what does it say? That the area under the curve, this area, is equal to, you don't have your teachers here, so you don't have to worry. Okay, x2 minus x1 divided by 2. I think so, right? Yes? You can use more complicated things, okay? Simpson, you can go higher in order, but usually this is quite okay for most cases. Or you can just reduce the time step, right? You can just simply use a smaller time step for that. Now there is one challenge by doing it like that. What is the challenge? Okay, let's say we are at time, let's say that equation, we are currently at time I, okay, time Ti, and you have production Qi, and you want just to compute delta, let's call it was gas, okay, delta Gi, or delta Gi plus 1. So you have different times, time I plus 1, and you have Qi, and you have GPI, and you want to calculate how much you produce. I think here we have put it, we put it here actually, and you want to calculate delta GPI to calculate GPI plus 1, right? That's what we have done the other day in class. We said GPI plus 1, the cumulative production, everything that I have produced from the beginning of time, is equal to the one from the previous time plus what I have produced in the year. So in the rectangular approximation, we have said that delta GPI will simply be Qi times Ti plus 1 minus Ti multiplied by the number of days per year, right? That's what we did last class. Now our new proposal, we are saying that delta GPI is Qi plus Qi plus 1 times Ti plus 1 minus Ti divided by 2, right? And we said that's going to solve all of your problems, that's going to make you a happy person. What is the problem? What is the problem there? How do I calculate this Qi plus 1? I need, just maybe make it, let me just make it a table so it looks more like organized. So here I have time, Q, GP, delta GP, then I have PR, The thing is that to calculate this Q, you need this P. And to calculate this P, you need this GP, right? So it's an implicit equation, right? You are depending on the same thing that you want to calculate. Here, you need this guy to calculate this GP. You need this GP to calculate PR, and you need PR to calculate Q. And you need Q to calculate delta, and you need delta to calculate, so it's like a snake eating, its tail. So nothing to do about it. You have to, in that case, that's an implicit method. Okay, it's in an implicit integration method. That requires iteration, okay, iterative solving. Okay, in a very roughly said, you have to assume a rate, calculate the PR, calculate the rate, and then see if they are the same. If not, you repeat. But it's a bit heavy so keep that in mind. I can make it, and it's important to make a better approximation of, trapezoidal. Basically, I make the approximation, like a straight line, and then it's much better approximation of how much I have produced in that interval, especially if I'm talking about, I do my predictions every year. But I have to pay this price of it becomes implicit. Okay, there was one more comment, or I think I have two more. So I have already published the exercise, and it's I hope it's a lot of fun for you. But you have to make a few, and that's typically something we make. We try with different plateau rates and different number of wells. So you have to do a few things here. So what do you think happened intuitively if you produce with a higher plateau? So let's make here the base case. You already know how it looks like, time and Q of the field. The base case looks something like that, and then declining. And here we said this is around 20 years. What will happen if I produce a higher rate, a higher plateau rate? Shorter plateau time, yes. Intuitively, right? You think, okay, intuitively, if I use a higher plateau rate, I should reach the end of the plateau sooner. And then what can I say about the decline? The decline faster? Why? Yeah, you will have to, that's something, those are part of the questions you have to answer in the exercise. Okay, if you do it, how is the plateau height, plateau length, but typically it occurs a bit faster, okay, a bit sharper. Now, is the amount of what we call GPU, right? Remember what was GPU? GPU was cumulative production, ultimate cumulative production of gas, because G stands for gas. Okay, N, if it was an oil field, we will use NPU for oil. So GPU is the integral of this rate of the field from 0 to abandonment time abandonment. So, yeah, and what if we use a shorter plateau? The same thing, gives you a longer period and maybe a longer decline. So one observation is that the higher the plateau, the shorter the plateau. Now keep in mind that in these three cases, probably the cumulative, that means the area that I have under the curve, now it's going to be very messy. Okay, until this point here, it should be, usually should be very similar between them. Okay, so GPU of the first option, let's put option number 1, option number 2, and option number 3. Okay, so the GPU of the first option should be more or less similar to the GPU of the second option, and should be pretty much similar. If we don't change, we just change the plateau height. Okay, the system is exactly the same number of wells, the same reservoir, the same minimum pressure. So the integral should be more or less similar. And that approach is sometimes used by people from outside of petroleum, from statistics, people looking at decline of oil production, from economists. They use that assumption. It's a very strong mathematical concept. Okay? And they use it to be able to predict, without using reservoir simulator, without using anything else, you are using it to predict, you know, for the production profile for different plateau heights. Also assuming exponential decline. Okay, so in that case, what can we say about the areas? Let's look a bit about the areas. Okay, let's make this one green. Okay, so in option 2, the areas should be the same, right? The areas between option that I have in 1 and the area that I have in 2. But you can see that they are produced fundamentally in a different way. In one of them, I have early production, and then it should be, you know, it's already included in you know, in the area of the red one, right? So here it tells you that the area that I have produced here early has to be equal to what? If the two areas are the same, if the two GPs are the same. To the difference between this curve and that curve, right? To the rest of that. So this, like additional plateau production and this tail decline, this area should be the same as this area. Yeah, that's what the equation is saying. So it's also to be said in a more, that's from the mathematical point of view, but from the logical point of view, you are producing the same, but here you are producing more initially and then less after. And in the other approach, you are producing less initially, but you're producing more after. But the two areas should be equivalent. Okay. Now, the last comment about the exercise is on what happens when we operate at constant pressure. If I don't want to produce in mode A, but I'm producing in mode B. Just simply decline, just simply constant pressure mode. Okay, maybe should we change it here? How do we modify the sheet to, you know, to calculate the rate to be now operating with pressure, not with rate? Let's first put a number here. Let's say I'm operating the field with a pressure of 200. Now, the rate of the field is going to be how do I calculate it, the rate of the field? Well, I can maybe make a trick, right? I cannot call this, I can just take away the potential name. Yeah, and I can take away here field, the potential. And then I simply can just take, instead of that pressure, now I take this pressure. Okay. And I unblock it. Okay, and the Q of the field simply will be equal to, yeah, it will be the same variable. Okay, and something happened. What happened? But still I don't know why. Don't see the error. Here the decline is very fast, okay, so you don't see, well, the comment was that if you're operating in decline mode, or in constant pressure mode, if you have a constant pressure, you typically have, some curve with some sort of a slope. Okay? You have a behavior of a curve, but the pressure that you have can change with time. So the decline of that slope, the value of the coefficient of that slope, if you have, for example, an exponential function, it will depend, the decline or the coefficient or the shape of the slope depends, and we are going to see it right away with an example, depends on this PWF, okay, the operating PWF. And that essentially means that every time I change PWF, this constant is different. Okay, that means that if I try to use the same, what I will do if I have a collection of points, right, with time of a field, and that many people is doing, they simply just try to fit a line that goes through all of them, right? But essentially, by changing, if I had any change for some reason, I have any change of PWF in time, that's going to cause that the coefficients are going to be essentially different. So I'm trying to cover, and maybe I managed to find a function that falls through all of them. But essentially, if I have a change in PWF, I should have like a function in segments, that I have one coefficient is valid for each section. Okay, so keep that in mind. We're going to go back to that in a few minutes. Okay. Yeah, should we take a break? Yeah, 10 minutes. Okay. I just want to say a short comment on the IPR equation used. And yeah, so the equation we are using, this back pressure gas equation, we are going to be using throughout the course very simple equations that we can use in Excel. Here you can use MATLAB, but we are not going to be using very heavy reservoir simulation or tools. And the reason is I just want to focus more on the results and on the method than on the equation itself. Then after that, you can work with more advanced tools. You can program your own simulator, but just I think to understand the fundamental concepts is better not to put too much complexity in the model and put more in the on the analysis. So this equation, there are a few limitations for that. Okay, CPR, and one of them I have to be either in the steady state or pseudo steady state regime. Okay, sometimes is people use SS or PSS. And the next limitation is that is an equation for low pressure. So and low pressure might be something around 100 bar. So it doesn't exactly, I shouldn't be able to use it for our case. Okay, our reservoir pressure was 270, but we did it anyhow. Okay, so just be aware of that complexity. And to go a bit more on the many IPR equations, they are actually developed for that regime. Okay, and if we look at the well, okay, let's say we have a vertical well, and we have some formation here, some reservoir. And we have here are the wellbore ratios, and we have some external radii of the formation. And here we have our wellbore. So if let's make a plot down here, or we can make it, let's make it here on the side, where we are going to plot pressure along R. And we're going to make the plot from RE to RW. When everything is, I have no production, everything at time 0, everything is closed, everything should be at the same pressure. Okay, we are making, that will be PI. Now, when I start production, and let's say I manage somehow to keep the pressure in the wellbore constant, I have to use to allow flow from the wellbore, from the formation towards the wellbore. I have to have a pressure here which is less, right, than this initial pressure. So let's say I bring it to, let's say, this number, okay, PWF star. The instant when I open to production and I fix that pressure, then the profile, this pressure changed, but the rest of the reservoir doesn't realize what happened. So you have, if you plot the pressure, you have like an extreme big jump, and then the pressure will be exactly the same. What happens here is that the piece of rock which is next to the wellbore has a lower pressure, and then the rock just next to it, adjacent, has a high pressure. So you have a pressure differential, and you will have flow towards the wellbore. And because of that, the pressure of farther away will be also reduced. So that, let me make it, maybe the color is not so good. So this will be time 0. This will be time 1. But with time progresses, it's like more area far away from the wellbore is being affected. The pressure is reduced deeper into the formation. So you might have something like that. And then you might have, let's make one more, something like that. Okay, and that's for time, let's say 3, and that's for time 2. So all of that regime, we know it, we call it the transient regime of the well. So that all the time until I reach the boundary. Okay, until I reach, and the boundary, until that change reaches the boundary. So the time, let's make it here, time from T0 all the way to T, let's call it T4, and I ran out of colors. Okay, T4 will be maybe something like that. I have a change, but it will be extremely, because it's far, far away. Okay, the well bore, yes? Yeah, should be opposite. Somebody's awake. So from so that what we're saying is T4, okay, and T4 is when the pressure perturbation, okay, when or what you will say also the rate, okay, you have rate every time you have a pressure change, you have a rate from one position to the next position. So when rate changes, reach the boundary, okay, that I call the transient regime. And that depends pretty much on the permeability of the formation, among other things. Okay, but if it's very you know, the pore sizes are very large, then that time will be very short. Okay, that time, transient time, sometimes people call it TSS or TPSS, time to, that means time to steady state, because after that I just have steady state, and this is time to pseudo steady state. Okay, so and that so TSS is a function of, among many things, of this K, which is permeability. So be careful. If your permeability is very low, it will take a very long time to reach the boundary. And if that happens, let's say if that happens in a matter of, it can happen in years, 20 years, 5 years, 20 years, you cannot use an equation for the other two regimes. You cannot. Okay? And that's the case. So let's make it here a comment. Okay, I shouldn't be writing too much, but if TSS or TPS is long, okay, that means in months or years, okay, then I should use, you know, I cannot use an equation for steady state or pseudo steady state. And that's very typical for this tight, either shale, gas, shale, oil. That's typical shale, gas, shale, oil, and also tight gas and tight oil. After that happens, you have two options. One of the options is that pressure at the bound is somehow kept constant. And that can happen if you have, for example, if you see that well from the top, you have one well, okay, and then you have another well where you are injecting, okay, where you are, let's say you're having water injection. Okay, so that's a oil producer, for example, and here you have a water injector. And that's this RE. So I'm keeping it with this injection, I'm keeping that pressure always constant. And that is, so that means after, now it's becoming very messy. Okay, after TSS, or after the transient, if P at RE is constant, then is what we call steady state. Otherwise, what will happen is that you will enter into decline. Okay, the pressure will start to decline. And then it will remain the same shape, but it will simply become smaller and smaller. It will be like a scaled version of that. And that's what we call the pseudo-steady state, because it keeps similar shape, but actually the pressure at the bound is reducing and then goes down and down and down. Okay, so this is the pseudo-steady state. Now, one more step, okay? If you are in the steady state or pseudo-steady state, you can remove the time from the whole equation. If we are in the transient, we have exactly to be tracking this interface. What happens with the perturbations in pressure is messy. Okay? But if we are in the pseudo-steady state or in the steady-state regime, we can take just time out of the picture. And we can say that the rate of the well, so in SS or pseudo-steady state, the rate of the well can be simply a function of PR and PWF. We don't need to include time. However, in the transient, then the Q of the well has to be a function of initial pressure, PWF, but also of time. And that complicates quite a lot, you know, the treatment, the estimation of the rate. So just to warn you that the equation we were using is in the pseudo-steady state regime, and that's why we were able to take out time completely from the picture. Just using our time variable, the variable that introduces time is reservoir pressure. When that goes down, that means I'm having, you know, a production. And truly, if, let's say, you're producing a field, you open, let's say, you start producing a well. The transient typically is very short, few hours, a few days, but then for the rest of the month, for the rest of the year, most of the outtake happens in the steady state regime. So it's a fair approximation simply to use that equation, if the transient is short. Okay? If the transient is large, then you cannot do that equation anymore. You have to use something like this. More or less clear? Yeah. Okay.
But in the graph, if that is the pseudo-steady state, then what is the steady state?
The steady state will be simply it will remain on this curve. Because that pressure is kept constant, that pressure in our example, we are keeping it constant, so it will stay always like that. Okay. In the pseudo-steady state, we have the change. That pressure is changing because you are, let's say, it's closed. Typically, I have a closed boundary, so I'm draining material, and that pressure is going down. So every time you open a well for production, you will have this process. If it happens fast, you're lucky. Okay, you can use this equation. You can relate rate with reservoir pressure. If it happens very, very slow, you're not so lucky. You have to do something else. Okay. To look more into, so you're going to make this exercise, right? On this exercise? No. Yeah. You're going to make that exercise, and you have a lot of observations you have to make, a lot of cases you have to analyze, and from there you have to, you know, get to some conclusions, some observations. But I just want to use a case that we can make analytically to show some of the same, okay, that we can do it here in class. And then you can corroborate and verify with the exercise. So let's assume we're going to use the case of undersaturated oil reservoir with we're going to have an underground and an underlying aquifer. large, and we're going to say it's a large aquifer. And we're going to make an assumption that the oil will remain liquid throughout the whole production of the field. Because the aquifer is so large, actually this aquifer is like, you know, it flows into the reservoir such that such that it stays, you know, above the bubble point. P reservoir is above the bubble point for the whole production time. Okay, and that means no gas in the formation. Actually, you know, it should be also PWF is also greater than PB, bubble point pressure. The next assumption we are going to make is that so for this type of reservoirs, I can say that PR is an initial PR, initial reservoir pressure, minus a constant times the cumulative production, how much I have produced. We're not going to make the derivation here in class, but it's similar to something I do for the gas. I have a tank where I have some oil here at the top. It's like a tank approach. Then I have water. Okay, and then I have here my pressure gauge, reservoir pressure. And I start to drain this. I start to produce that oil, and that's the equation the reservoir pressure follows. It's an initial pressure, and you have a decline constant, is linear, and NP. If you plot it, how should it look like? No, that's not time, but that's NP. That's how much I produce. And that slope is A. Okay, and A, if you are interested, what does it have inside? Okay, A, I'm going to write here the expression, but it's not really that important. Okay, A, actually 1 over A, or A, is BO Okay, just putting it here for fun. Okay, so if some of you wants to see what it has inside. But if I make my material balance equations, I know what I'm taking out, only oil, and I am assuming both of them expand. This liquid, you know, is not incompressible. Liquid, if I put pressure on the liquid, it will have some compressibility. These are the C's that are indicated here. Okay, at high pressures, this C is compressibility. And I have compressibility of oil, I have compressibility of water, and I have the compressibility of the rock. When I apply pressure on the rock, believe it or not, there will be some, very little, but there will be some change in volume. And then you have, what is more important, you have this N, which was, what was N? What did we use N for? N is initial oil in place, right? Not that I can recover, whatever is in place, from what I recover. Remember, recovery factor is NPU divided by N. How much I recover from how much I have in place. So that tells you also a bit about the size. Okay, if let's say if N, okay, if N is big, okay, it's a big reservoir, should the decline be steeper or should it be slower? Slower, right? If you will say, if I take material, right, let's say I take 1 barrel, if it's a big volume, the pressure should go down very slowly. Yes. If I take the same amount but the reservoir is very small, it should decline very steeply. Okay, so that's what the equation is telling you here. And the other thing you have is the volume of the aquifer volume, because the aquifer is also expanding. So if I have a big volume of the aquifer, that also helps to such that the curve will have a easier decline. So that's aquifer volume. Okay, but you don't have to care too much, just you have that equation that depends on volumes and fluid properties. Now on the side of the wells, okay, wells are operated with electric submersible pumps. Okay. Okay. Which is simply a pump that I put inside a well. Okay, here at the end of the pipe I have a pump such that the fluid comes out of the formation, goes through the pump, and then goes inside this pipe, inside the tubing. And here I have the constraint that the PWF, there is a minimum. Just like in the gas in the previous example, okay, there is a PWF minimum. And that minimum pressure is given in this case by PWF minimum is the bubble point pressure at that temperature. Because I don't want to get any gas into the pump. Okay, I just want to get purely liquid. And I say you can change it from any value, but the minimum you can reach is such that I don't get any gas bubble here. I don't want to get any gas entering the pump because it won't work. So the production from this well, I can say that the Q of the well, the rate, will be J times PR minus PWF. When I have, this equation is valid when I have only flow of liquid. Flow of liquid only. Okay, now to make our equation, or to make our its analytical development, so the equations are fairly simple, right? I can introduce one equation inside the other. In this case, I can say, so let's say the Q of the field, right? It will be N wells times J PR minus PWF, right? And the Q field max, okay, or Q field potential, what we were discussing before, will be equal to the same expression, but now I have to substitute PR was PRI minus A NP minus PWF minimum. Yes? So we have an analytical expression for this potential that we were calculating before. Now we don't have to calculate every time, but we can have an analytical expression versus NP. How is that potential changing with NP? let's rearrange a bit the expression. So Q field potential, and I want to put all of that n wells times J PR. So let me make the following. I'm going to put everything that depends on NP. So I have n wells times J times A times NP, and plus n wells times J times PRI minus PWF mean. Yes? So if you see here, and this I'm going to call M. Okay, it's like a slope called M. So Q field potential will be minus M NP plus, and what is this guy here? That's the maximum my field can produce at original state, right? The first day, when if I fully open the wells, I put them operating at the minimum pressure, that's the maximum I can get, right? So I'm going to call that Q field potential O, original. So you're saying, well, why to go to so much trouble, right? Why are we doing this, okay? And you see it's just a straight line. So the potential of the field, Q, is simply reducing linearly with NP from QF, PO all the way down. Okay, for this particular case. Now you remember what happened when the plateau finished. How did we know that the plateau finished in our Excel sheet? Yeah, but why? What happened first? We had a comparison, right? The rate got less, but because we were making this comparison, is it greater than the potential? I can produce. Is it less? I cannot produce, right? So how can I use that expression to see when the plateau is going to finish? When is equal to the potential, right? When the field is equal to the potential, let's say I have a Q plateau, right, that I want to try, plateau. When this one is equal to the potential of the field, that means that's the end of my plateau, right? Okay, when these two are equal. So I can say, I can apply the same equation, right? Minus M NP star, okay, because the end of the plateau will happen after I have produced some amount of oil that I call NP star, plus QFPO. At that point, no more plateau. After that, if I keep producing, increasing the NP, I will enter into decline. Before that, I'm able to keep production in plateau. You know, many people get it, maybe 30% got it now. Maybe 30% are confused, think they got it, but are a bit confused. And the rest, you know, didn't get it. So I say just, you know, you have to think over a few times. It is not simple to comprehend. So the nice thing about this equation is that I know that in plateau, remember, from 0, well, for NP 0, all the way to NP star, I was producing in plateau mode, right? That means that I can express NP star as the Q of the plateau times the duration of the plateau. Plateau duration, right? Times this number of days per year. not after. After NP start, then you start having decline, and then you cannot do that. But before that, if you were producing in plateau, if from 0 to NP, the Q of the field was simply Q of the plateau. Then I substitute that into this equation, okay, to find out the plateau duration. So let's see, Q, and here you have to help me, I don't make any mistakes. Plateau okay, and then I have to clear the number that I want is this one. Okay, that's the duration that I want. So then I have QF divided by yes?
No, there is no minus.
There is no minus, okay. And then the next step is, then I get, I can take a common factor, M, then I have QFPO divided by Q plateau minus 1, and here I have the number of days, TP. Yes? Now let's return, okay, the definitions I had made initially, okay, these two, to see how, first we want to see how, remember, these are representing different things, the number of wells I have, the productivity of those wells, and then the volumes that I have. There are three things that I have in this equation. Okay, so I want to see how each one of them affects the duration of my plateau. And let's see that we have some ideas like logically how they affect, but we should be able to get them from the equation. So QFPO was PI minus PWF mean, right, multiplied by J multiplied by N wells, and divided by Q plateau that I have, that's an input, right? That's something I decide. Okay, and 1 over M was NW times A times J, right? And 1 over N days. Okay, now we multiply, and what do we get? Let's leave a few things out. So 1 over A. Then I take 1 over N wells times J. And this should minus 1 shouldn't be here, right? Okay, I think so. If not, you have to you have to find out. Okay, but let's say, what happens if I use if I have a bigger reservoir? The first thing, you know, this A depends on the initial oil in place, and if N becomes bigger, then A becomes smaller. That gives you, according to that equation, so let's say bigger reservoir, okay, let's say higher N, okay, that gives you a smaller A, and that gives you a higher TP, which makes sense. Okay, the decline will be, yes or no? Yes. Okay, the next one, what happens with number of, if I increase the number of wells, more wells? The negative part of the TP becomes smaller, right? Therefore, the TP is also increasing. If I put more wells, I should expect that plateau becomes longer. Then, if the wells are more productive wells, higher J, you have the same effect, right? Higher TP. If PWF, if I say lower PWF mean, okay, I managed to lower that pressure somehow, then also increasing TP. And finally, if I decide to use a bigger plateau, okay, higher plateau, what should happen? Higher Q plateau. Then this one goes down. Again, you have to have some time to think, but basically everything, keep that in mind, everything plays some part in the plateau duration. Everything. Decline, the size of the reservoir, the productivity of the reservoir, how many wells I have, what is the productivity of those wells, and what is this minimum pressure. Okay. And if you make the analysis with a more complex system, you do it including flow lines, pipelines, more wells, there will be a more complex equation there. But everything is in there. Okay, everything is on that equation. And that's what you're going to now evaluate with your gas case. Okay, with gas we have the material balance equation is not so nice. It's not like that. So we cannot use this analytical development. But actually, those are some of the things you have to evaluate for the gas case. Okay. Now, let's see if we can use the same equation for post-plateau performance. Post-plateau rate, okay? Can we use the same equation or can we use this potential somehow for the post-plateau rate? What happens if you remember, or in our exercise that we were doing, right? After I reach the plateau rate is equal to the potential, the Q of the field versus time. After I reach that point, I start the decline, right? But how was the rate of the field in all of this time, from this time on? Was equal to the potential, right? Was equal. If I cannot produce what I want to produce, then I produce the maximum that I can. And the maximum is this potential. So for this period, I'm producing the Q of the field is equal to this Q of the potential of the field. for all of this period. For this period before, the Q of the field is less than the Q of the potential. So we should be able to use the equation for that. So let's relook at the equation that we had, that was this one, okay, and try to use it for the post-plateau period. So I'm saying Q of the field potential was how much? Minus M NP plus Q of the field potential original. Now I have here if you remember what was NP? NP was the integral from 0 to t of Q of the field, right? dt. Yes? Now I have here two very clear parts of this NP. I can say that I have one from 0 to Tp, and I have one from Tp to T. That's the plateau period, and that's the decline period. And here I say that basically is Q plateau, which is constant, times dt. And this will be Q potential, right? That will be simply Q of the field potential. We already agreed at that time, after Tp, it will always be operating at potential. So we can substitute that expression here, and we obtain QFP minus M times Q plateau Tp. And here we have this conversion factor. I am not going to put it, plus integral from Tp to T QFP dt. Yes? I hope so. Oh, yeah, I'm missing this term, right? QFPO above. And I'm missing the M. I think either I'm asleep, but you are more asleep than I am. Yes? So I had an expression, right, for the end of the plateau from before. If I substitute that expression here, let me see how the expression was. Tp, I think, was this expression here. This expression. If I substitute that expression, I end up with the following equation. QFP, that you have to do it, Q plateau minus M Tp to T QFP dt. Okay, if I substitute Tp in here, and Tp was, let me just put it here so you have it. Tp was 1 over M Q FPO Q plateau minus 1. Okay, and I have this time, the number of days in a year. Okay, I have it there someplace. Okay, so if I substitute this guy here, so now that equation, can I solve that equation? Yes? What is a solution of that equation? How do I solve it? Yeah. We have to use this integrating factor, right? I think so. But well, that you have to solve somehow. But I say a solution of that equation. We can ask. You can ask your friends that are studying mathematics. A solution of this equation is that Q of the QF potential will be Q plateau times e to the minus m t minus tp. Simply from math, okay? From solving that equation I have there. I have the variable I want to clear is this one and this one, and then I clear it, and that's the solution I find. Okay? And you see I have, when time is tp, this disappears. Okay, so I have simply that I have plateau. Exactly at time tp, I will have the plateau rate. And after that, I have simply an exponential decline of that plateau, which is very nice. And what is affecting, so that tells me, when I look now and give me exactly the profile that I was expecting. Okay, Q of the field versus time. First it will be constant all the way to Tp, and from here I have an exponential decline, where you see the coefficient of that. What is affecting that decline? Okay, that decline is affected by, if you remember, m was A times number of wells times J. Yes? Okay, so if you have a bigger reservoir, let's make again the same thing. If I have, if n is big, then A is small, therefore the decline will be much smoother. Okay, so you have a smoother decline, or like a longer decline. What happens now if the number of wells increases? If I put more wells, if I drill more wells, then this m is going to increase, right? Therefore I have a sharper decline. If I put more wells, then I should expect the decline very sharp. And if I increase the productivity of the wells, if J is increasing, then M again is increasing, and I have the same effect, sharper decline. And you have again all factors affect on the decline. Okay, all factors affect on the decline part. Yes, I think that was. Before we close, any question? Many questions?
What is the first thing?
The original oil in place. If n is high, A becomes small, and then the decline is much longer. The size of the reservoir. So just it's very simple. Okay, we started with a very extremely simple case. You don't have it almost any place. There are only a few fields. But by doing that, I can do it everything analytically, and I can analyze exactly what affects. First, I can calculate the profile for plateau and decline, and I can see what affects the plateau phase and what affects the decline phase. Okay, but you will have to do that for a more realistic case. Okay, see you tomorrow.